In the last class, we started to present the notion of using transfer functions and essentially using the Laplace transform to get to a transfer function as a way of representing a system's behavior really from this kind of input-output perspective. And that becomes important here because this alternative approach that we're going to talk about here, state space, is really a slightly different way of still showing input-output behavior, but also revealing how the internals work a bit more. And so from a transfer function point of view, we specify G, and that transfer function maps the input signal to the output signal. And it has all the dynamics built inside, but we're not explicitly kind of observing them or keeping track of them. So what we're going to say is that in state space, we're going to be paying more attention to the state variables with the idea that the output that we actually see is either some subselection, like one of the state variables, or some combination of the state variables that are inside. So in some ways is kind of, we think about this as being looking under the hood in terms of what's actually going on internally to the system. We're going to take a look at the spring mass damper later, and there are observable, the output that we've been using so far has been the position of the block. What we're going to observe there is that another state that's kind of internal, one of these internal state variables, is actually the velocity also. And so even though we don't get to observe the velocity of the block, it is something that is changing, and it changes according to some rules. And so that's what the state space is going to be able to specify, that the input-output behavior that the transfer function uses does not explicitly specify, despite the fact that it is there in the math. So one of the things is an undergraduate course in control like this often focuses entirely on transfer function, and a graduate program often will focus on state space. And so what we're doing here in this course is showing you a mix of both so that you can appreciate them, and also so you can appreciate the connections between them, which is often lost by taking one course on transfer functions approach and one course on state space approach. So when we think about representing a system in terms of its state space representation, what we're really doing is we're trying to represent an ordinary differential equation as a collection of coupled first-order differential equations. And so we've already seen some examples of when this is already true. But the idea is that by having a system of differential equations that are coupled together, we can represent that in vector format. And so we're going to collect all these states in a vector, and now this becomes a first order, so it means the highest order derivative is just one, and we just have one system of these equations. And so we'll talk about exactly how to do this in different contexts, but the idea here is then that this x variable represents multiple things. So we could have a vector that has multiple entries inside, and the time derivative of each one of those can be expressed as a vector valued function. And so that is the function that specifies the rules or the dynamics by which this system operates. So, and that function could take states, it could take inputs, and it could also explicitly depend on time. This is about as general as it can be, and so we're going to be particularly focused on the simpler case of the linear system, just like we talked about for the transfer functions. Again, there could be some sort of function, which could be this function that maybe takes in either or both of the states and the measurements. And this is essentially telling us how we measure our states and possibly inputs and get observable things, the outputs that we actually see. So that's what the sensor could be measuring. And over here, we just have kind of some fancy mathematical notation just to be precise. And really what this bold symbol R just means that it's a real number that has n elements in it. So this means that this x at each time is a vector of n elements, and this u, this input, is a vector of m elements, and this the output vector is a vector of p elements. And then that this is saying this function takes in something that has a vector of n elements, a vector of m, a real number, and produces a vector of n elements. So it's just a way of being precise. Again, we'll be focusing on a much more specific case in this class, and that's what the next slide's about. So when we look at state space systems for this course, we'll be looking specifically at cases that are like what we've talked about before for transfer functions, linear and time invariant. And this gives us these nice superposition capabilities that we observed with our systems from in the last class, as well as this time invariance, which means that the input affects the output, but it doesn't change depending on when you apply that input. So the way that we can characterize then a LTI, or linear time invariant state space system, is through 4 different matrices, and oftentimes we don't end up having this D matrix, so it's often 3 different matrices. One that represents how the state affects the rate of change of the state, one which is the mapping between the input and the rate of change of the state, and then this is the output or observation matrix that tells you what combination of states produces our outputs. So simply by specifying these matrices, which could depend on time if you wanted to. In everything that we do, we're going to be time invariant, which means that A, B, and C, and D don't depend on time. For what we do with transfer functions, in this course, we're entirely looking at single input, single output systems. So sometimes those are called CISO, that acronym. And that is really the case where you have one input and one output. And you can use a transfer function approach with multiple input, multiple output, or the MIMO case, but that is not covered in this course. That's when you essentially fuse together linear algebra and transfer functions at the same time. The nice thing about these CISO systems is that we deal with matrices and linear algebra when we talk about state space perspective, and we do a Laplace transform and transfer functions when we use the transfer function approach. This last slide goes a little bit beyond what we need to use in this particular course, but it's useful to see, I think, because this is something that connects and helps us understand how we get an LTI model from a nonlinear or more realistic system. And so one of the ways that we do that is through the process of linearization. Many of the models that we'll use in this course have actually come out of linearization because, in general, systems end up behaving non-linearly, and so when we try to study them, we'd like to simplify those models sometimes in order to apply some of the techniques that we have in this course. So what typically we do is we find a spot. I'm going to call it an equilibrium here, but essentially this is just some state and some input set. So along some trajectory of the system, we're going to end up linearizing that. And what we're going to do is we're going to take derivatives. And so the idea is that f is a vector valued function. This takes in these parameters, but then the output of that is actually a whole function, and that describes the derivative here. And so what we're going to do is we're going to evaluate that function, that vector valued function, and we're going to take the derivative at all the different x's, the states. And that's going to compose the dynamics matrix. So you can think about f as being a function that has f1, f2, up to fn different entries inside it. And so when we compute this matrix right here, we're going to be computing elements like df1, dx1. So that's the first element of the function with the derivative of the first state. And then we're going to do that same df1 with respect to the second state. So that's dx2. And the first row will finish with df1 dxn. I probably should be using curly d's because these are all multivariable functions. So that's the last state that we have. And then for each row, we'd increase the index of f1 until you get to the bottom where it'd be dfn over dx1. And then you'd fill out the rest of that row. So you'd actually be creating a full matrix that describes how the states then affect the derivative around this particular point. And one of the important things is you're going to evaluate this derivative at this nominal operating point, where x and u are at these nominal values, x bar and u bar. So we do that for all of these different matrices, and this is really the same idea as taking like a tangent plane, but we're doing that in this higher dimensional vector valued functions f and h. And so that's a way of mapping from nonlinear to linear. Again, we won't use this explicitly in this course, but it's we'll get a number of our models come out of this process that allow us to use our linear techniques. So now we haven't really talked about how you get into state space form, and so what we're going to do is we're going to do that through a series of examples and slowly build those up to make them more and more complicated.